Okay, good afternoon. Let us start sorting. So today probably, as you can see, we go into a few more or less simple sorts. And typically, all we will have to do is to take a sequence of some simple data, typically numbers or characters. Each character is a number, so it does not matter, and sort them. So we'll have no special extra data structure. The data structure we use is very trivial. It's a list or array, something which can be indexed. So it's more an array than a list. And at the beginning, we'll have some jumbled sequence of numbers or characters of anything, and then what we have to do is to produce sorted sequence. So you say that's not a big deal because, well, why? Because it's easy to sort anything. You understand what should be the first element, what should be the second, the next one, and then you step by step build your sorted sequence. On the other hand, strangely enough, there might be some different approaches to this problem, which sometimes surprisingly are quite efficient. So that's what we will go and try. So we'll start with a few examples. There is a selection sort, and it works in that most intuitive way I've just mentioned. You just scan your array and find the element which is the smallest. Evidently, that element belongs to the beginning of the whole sequence. So what you do, you put it there trivially, and because you are in some, let's say, limited space, you swap that element with that element which was originally at the first place, at the beginning of the array, I mean. So you've got it, and now we've got the smallest element at the beginning, and now you might say, well, now we can go recursive, because now you have the rest of the array, which again has to be sorted, and you apply absolutely the same strategy. So that's what you do: find the next smallest element and put it nicely at the second place by swapping, and in the remaining part of the array again find the smallest element, and so on and so on. The method is completely obvious. Therefore, you say, aha, so now after a while the array is sorted, as you can see down there, in some step with index k. In this case, it's about 2, 4, 6, in 7th step, or I don't know, 6th step. So you do again some of the same stuff, and finally the array is sorted. And we can stop talking about sorting now, because everything is sorted. Fortunately, or maybe unfortunately, depending on your point of view, that's not the best way how to sort a sequence. Strangely enough, let's see. Before we talk about why it is not the best way how to do it, just to more formalize the stuff, we've got the code which shows us what's going on. For obviously there is a loop which is the main loop, which goes through the array, and as we built that sorted beginning of the array, which is here at the beginning, so that loop goes through all these k's. Let's say, excuse me, and in this case it is I. So we go from 1 to n minus 1, let's say, yeah, to n minus 1, not to the last element, but but last element. Why? Because then we, to the right of that element with index i's, we select minimum in the range to the right of I. We have to select the minimum element. That means you just scan the rest of the array and remember on which index there was that minimum in the remaining part of the array. You can do, when this is written in Python, as you can see, you can do the same with slicing, but we don't do it. We don't write it with slicing just to point out exactly what's going on, even for people maybe who are less familiar with Python or so. So this is more primitive. So those of you who are more Python enthusiasts, you have to survive with that. This is not perfectly Pythonic way how to write it. On the other hand, we want to convey an algorithm, not the Python itself. And that when you discover that minimum, so what you do is just put that minimum to its place. That is that swapping swap in the array, swap element on position I and on position which of that minimum exactly. So this last swapping is exactly this stuff. So now it's all right. We've got the idea, we've got the code, we can run it and sort anything we want anytime we want. On the other hand, all right, you say, and how long will it take? Well, what you do is you have to do that swapping, but that swapping is done in each run in each phase, in each step of the sort. It is done once. But before you do swapping, you must find which element to swap with the next one, with this t. So you have to scan the rest of the array, and as you could see, and that's more or less obvious. In fact, we are scanning repeatedly the remaining part of the array, and we scan it repeatedly and many times. You find A is the smallest element, then you scan the rest and find B. Next, you have to scan again everything in there to find D. Next, you have to scan everything there to find next is E, and so on. So we repeatedly, many times, go through the right side of the array, and we can just easily compute how many checks we have to do, because what does it mean in step k? We have to do n minus k tests, as they write here in this part of the array. So it is in one particular step k. So then you go and total this value, how many tests we do. We total that value for all possible k's from the beginning to the very end, k of the step. First we have those steps which contain a lot of tests, and the end we have a short end of the array, so just few tests we do there. So here we just total that. So this is a standard formula. And that's a sum of arithmetic sequence, of course. And when you do your algebra, you get this result, which is n squared, as you can see. So therefore, the whole stuff is not that much glorious, because well. Jump to the conclusion, because we'll see the test number of tests is proportional to n squared, and as they say here at the bottom, the asymptotic complexity is proportional to n squared. You might feel a little bit optimistic because we do just few moves. if, for example, if you imagine that those elements which we are sorting are really heavy, big pieces of stone or anything like that, which are very difficult to move from one side to another, then you might feel optimistic because you say, okay, in each step, we just take two of those stones and we exchange them and we do nothing else. So in respect of moving the elements. So moves in total gives us 3 times n minus 1, therefore y 3 times. But generally, before we come to 3, generally it is just linear in number of elements in the array, so that's the only positive side of the whole process. The rest is unfortunately quadratic. Why do they say just here this 3? Well, because when you swap elements, typically when you swap elements, that might depend on your point of view. If you've got Python, and if you swap elements, you take. How do you swap them, by the way? Or it is there. So you take array I and array j min, and you do this array j min and and array I. So this is swapping 2 elements. Swap, but you need this syntax construction which allows more variables and parameters on the left side of assignment language, of assignment statement. Sorry, other languages. In other languages, you quite obviously you need some additional extra variable where you store at the beginning your array I, then in your array I, you store array j min, and finally in array with index j min, you store the foo. So there are 3 times you move the element, 3 times you move some value to some other position in the memory. So they say the moves, how many times you move the element. You move it from here to there, from here to there, and finally from there. So the foo is that up this temporary space at the top. Move it there, move this, and finally all goes to the place of t. But that's not important. It is just some easy calculation, so we can in fact skip them. So you say, aha, therefore we have theta n squared, so the Complexities Bug is something like this. So when you've got your array, if the length of your array equals to, let's say 1 million, then you'll have the complexity or the number of tests. A number of tests then is proportional to 1 million squared, which is 1,000 billion, simply 10 to the 12. And again, if you can perform 10 to the power of 9 tests per second on some rather faster machine, there you are still left with 10 to the 3 seconds, which is roughly 17 minutes or so. So if you got some 1 million elements, which is not that big array, you should not wait a quarter of an hour to sort the stuff. So we need some faster ideas. Faster ideas, maybe faster idea. Yes, it's not guaranteed to be faster. Is the insertion sort. Insertion sort has a different approach. And it says, all right, let us do not look for the smallest element, but look at it from the whole problem from a different side, and let's build at the beginning of our array, let's build a sorted sequence, that is, which is increasing. Therefore, when you start and you take the first element, then it is by definition sorted because it's only one element. So you say, we have this beginning of the array that is sorted, and the rest is not sorted, but our problem is nearly solved because we have a piece of an array which is sorted, and we'll take care of the remaining part of the array later. And that's exactly what's going to happen. Now again, to avoid searching the whole remaining part of the array, they take just the immediately next element after the sorted part, and they try to insert it at correct position. So you say, this is O, so it might either stay there or move forward. And this O is smaller than T, so O moves forward, and T is moved to the right, and we have a bigger sorted part of the array at the beginning of the array, and we didn't have to scan the whole remaining part, which seems promising. Okay, so let's continue. And again, there is your sorted part. Take next element and insert it into where it belongs with respect to those elements which are already sorted. So B begins to the very beginning, and now you start seeing, so maybe there will be some problems because at the beginning we don't have to scan the whole array, but later in the process, when we are getting closer to the end of the array and the sorted part of the array at the beginning becomes bigger and bigger, then when you find an element, and you don't have to scan the right part, but now you have to scan the left part to find out where this element belongs. This A, where does it belong? You might say, well, but still that can be improved a bit, because we can find the place where A belongs by some binary search. For example, this part is sorted, that blue one is sorted. To find where A belongs will take logarithmic time that is considered to be fast. Okay, if you find that place where A belongs quite quickly, that's nice, but then what you have to do is to shift all the elements to the right. So as you can see, when you find in the previous step, when they found M belongs between K and O, so everything starting from O up to U has to be shifted by one element to the right. So that takes time. There is no way to get around it. So instead of searching, as we did in the previous algorithm, searching the rest of the array and finding minimum there, now we have to take a lot of elements at the beginning of the array and shift them. But at least it is not guaranteed that we have to always shift everything. Maybe we might be lucky and shift only some smaller part, which would be nice. But on the other hand, we cannot rely on that. So is it better or not? It is somewhat better than before. It is somewhat better than before. So first, let us check the figures. So what happens in step K? In step K, there is this best case when you find, okay, if for example, you this was not M, and if that was Z, then you would compare that Z with U, and that would be the end of it, because you would say then, we don't have to change anything and we can move to the next step. So the number of steps is big or small, depending on particular value of the element which we are trying to put on its place. So there is this best case, there is this worst case, meaning that we have to check all the elements, because, for example, next time when we take A, we check all the elements, and okay, maybe that can be smaller, that number of checks due to binary search, but the number of moves when we are moving the remaining blue elements one step to the right, there is always this number. So in the best case, you say, in the best case, we don't move anything, but we will see in the code that you, in fact, do some moves. Nevertheless, important information is that the number of moves is trivially small. In the worst case, the number of moves is quite big, because you have to move one step by one position. You have to move everything, which is everything blue, and also this element which is being inserted at the beginning. So the worst case is the same as it was more or less before. Therefore, the conclusion says, okay, in best case, we do small number of checks and small number of moves, and if we are lucky, for example, if the sequence is sorted, sequence, then in that case, insertion sort works in time proportional to in time O n, let's say theta n. So it in fact in effect goes through the array more or less just once, and that's it, and it is sorted. But it is the very best case, which of course we cannot rely that it will happen every time. Then there is this worst case, and that worst case is obviously quadratic, as we have seen before. And the average, the trouble with the average is that the average is quadratic, or expected, what expects more or less if the values, or if the array is randomly shuffled. So the average case does not help that much, and what to expect is again quadratic case. So we can do a little better than in the previous selection sort. With insertion sort, sometimes when you are lucky, you can do better, or if the sorted sequence, if the sequence is sorted or nearly sorted, or let's say nearly sorted, or for example just a few items displaced. You've got, for example, you've got 1 million elements, and you know that 120 of them are displaced and are somewhere else, and you say, okay, that would be nice, because that would mean that we can, in nearly or in linear time, sort it. That would be nice, but typically it does not happen all the day. So every day it does not happen. So you should be satisfied with it, with this. So we could do a little better, but we'll have to wait another few minutes before we arrive to really faster solution. Before we get there, there is just one reminder of a very old, very let's say ancient or antiquated sort, the so-called bubble sort. And that is, I don't know, it's not important, as we will see. It's not important because it is really slow, but what is what is important in it, maybe sometimes, is the code. You can code the bubble sort on 3 lines. So therefore, if you are in situation when you have no sort in your library and you have to concoct something which was sort, so you can write it on 3 lines. Which reminds me that I skipped the code for the insertion sort. So let us go there just to go through it step by step before we go to bubble sort. So insertion sort, what does it does? Again, there is the loop of those steps, and inside each step we have to find and make place for current elements. So this is our array. This part, let's say this part is sorted, and now we are at position A, investigating some value at that position. So you can say, okay, so that value should be inserted somewhere into the sorted part. So this part should be taken and go somewhere, who knows where. So that is this insert value, which is this one. And what we do, then j is set to I minus 1, so there will be j, and that j moves from this position back to the beginning of an array and check whether it is time to insert our value at a particular position at j. So exactly this is the check which is here. But obvious, of course, j cannot run out of the array. And while we are moving to the left, we take the elements, those sorted elements, and shift them to the right to make space for the insert value, which we will insert at the very end of the whole process. So there it is, again, quite very simple. And after inserting the value at its position, the loop body is done, and you can move to the next and repeat the whole stuff. So again, as you can see, rather simple. Let's move then to the bubble sort. Which is very particular, because it checks. Each time it checks only 2 neighboring elements. As you can see, they always just swap or leave them alone. Swap 2 neighboring elements, and that is because this is sorting developed for situation when your data is on the tape. With data, and there is one head. Sorry, read. Right. Head is there. There is some magnetic head, and the tape goes through it. So if you want to transport one piece of data from one position on the tape to another position on the tape, you must roll your tape in such manner that the corresponding part of the tape appears at the read-write head. And if you then want to go somewhere else, then you again have to rewind the tape. So accessing data, let's see. Data is a lot of tape rewinding, And bubble sort tries to minimize the number of rewinding operations. You don't rotate it to the left and to the right. Therefore, it always investigates only two neighboring elements. So it does not jump from here to here and then again back. No. You go from left to right. And what you do, you simply compare two neighboring elements, and if the second is smaller than the first one, you swap those elements. And you do it for each pair of neighboring elements in your array, and you go from left to right. That is, you are more or less rotating your tape in one direction. When you arrive there after this phase 1, you have done some work, and the result of that work is that the biggest element in the array appears at the end of the array. Always, whenever you compare two elements, the bigger of those ones goes to the right, and then again it is compared with the next element. So if T was the biggest element in the array, then it should be swapped with B. Then you move your window or your area of interest by one position to the right, and again there is this big element, which again, if it is the biggest, again is swapped with the next element. So it is like a big bubble which is going through smaller bubbles, is going up to in the direction in the direction to the end of the array, and after a while you might be sure that at the end there is the biggest element of the whole array is at the end. And then what you do is you rewind to the very beginning, and you repeat the process completely again with, of course, only that small change that now you do not go to the very end, because you know that at the end is the biggest value. So you just, in the next phase, you will stop on the but last position. And you do the same. So there are still here in phase 2, and go through everything, and that brings you to the end. And then you repeat this again and again, and each time, of course, you repeat it on a shorter and shorter unsorted beginning of the array, and after a while, that means after performing n-1 phases of this stuff, everything is sorted, and everybody is happy. Is happy depending on the result, of course, and the resume, as before, says, okay, how many steps did we have to do? Well, of course, in the first phase, we do n-1 comparison. In the next phase, we get n-2 comparison. I mean the phases, those are the phases. In phase 3, you do n-2 comparison. In the last phase, you just compare A and B, whether they are correctly sorted or not. So again, you just total this standard arithmetic sequence. You get theta n squared. So again, we did not do better. But if we are ever pressed to write a sort, any sort, we will write something like this, because it is easy to conceptualize and therefore also to write down. For those who are less fluent in Python, what the first line says, it says go from 1. It's an implicit parameter there is 1. It's a range of numbers starting at 1 up to a length of the array minus 1 and minus 1. No, excuse me, I'm telling you nonsense. This means something else. This means Yeah. This is the last position. So, no, not an easy stuff. That is the last position, and that is the position where we stop, where the last biggest element will each time appear. So that is that. So the the outer loop goes from the very end of the array. That is the first parameter. Excuse me, so we will stop there, and then in each step we will move to the right. So -1 is the step size, and because it is negative, we move to the left. And -1, the last one, this is the last one. And the but last one says that we have to stop when I gets to -1, when it gets out of the array. So that's just the syntax. And the rest should be more or less obvious, because now this range goes from 0 up to the last position, not including the last position. So go up there and check it. So all right, so bubble sort, bubbles, never use it in real life, but the idea is, well, the idea of sorting, let us say. Then this guy invented in the year 1962. 1962 invented this quicksort. So let's see quicksort, and it is quicksort for good reasons, because in most cases it is really quick. It is based on typical paradigm called divide and conquer, which says if you've got a problem, then what you do is to take a problem and divide it into smaller pieces, delegate those smaller pieces to various other helpers, maybe, or to some other people. Let you do that, you do that, you do that. When you are ready, bring it to me back. I will put it somehow together, and the problem will be solved. So that's exactly this idea here, just more cartoon, some kind of cartoonish presentation. Your problem is big. You divide it into smaller problem, or let somebody else solve those smaller problems, because when you are dividing the problem into smaller problems, then you are important, and those are just they have to do what you tell them. And when they solve their particular problems, they bring their solution back, and you say, aha, there is a solution, I can put it together and have the final result. So let's see how it works in practice. It is totally abstract, no one knows what's going on, but here it should be more or less obvious after a while. So what's at the beginning? At the beginning we've got at the top the array, which is again unsorted, and now with the idea that somebody is able to do smaller work, we say, okay, let's take our array and divide it into small and big values. That means move small values in whatever order, move them to the left side of the array, and the big values which are in the array, move them into the right part of the array. And of course the whole array still will be totally unsorted. There will be the only additional idea which says, all right, but if those are big values and those are small values, that means that everything which is among big values is bigger than anything which is among smaller values. Therefore, if you go to those big values, which you can see are exactly those which were originally there, M, R, T, O, U, and Z, and the smaller are the remaining ones. So if you are able to rearrange your array in this way, then in this moment, if you have those helper pairs persons, you can say, okay, go and sort this left part, and somebody else go and sort that right part. That is, ask somebody to put this in order the left side, in order ask somebody else to put in order the right side, and when they do the work, then everything is done. The problem is solved, because if somebody comes and solves and sorts this one, and somebody else sorts this part, so first this will be increasing values on the left side, there will be increasing values on the right side, but the smallest of the big is still at least as big as the biggest element in the small values, because they are all bigger than all smaller. So when that happens, the whole problem is solved. And again, of course, those people to who you delegate your smaller problems, they will of course work in the same fashion. They will again find somebody to do for them the smaller parts of their problem. So they again say, okay, we will work in the same way, because we are in a recursive function. I will divide my piece of data into small values and big values, and I move the big values to the right and small values to the left, and ask somebody to sort it. And when that is done, I will just return my results. So and this process goes recursively to smaller and smaller pieces of the array, and when the recursion comes so deep that the piece which has to be sorted contains only one item of data, and then of course one item of data is sorted by definition, so they do nothing and the whole recursion stops and starts returning. So if everybody does their work in arranging their part of the array into small and big values, of course, which are small and big in their respective part of the array, so then everything will be done. When you divide into small and big into this part, you know nothing about the right part, what's going on in the other part of the array. It is not important whatsoever. So that's important, that you can just concentrate. You don't need outer more information from about the rest of the array, so you can be completely local. So when everything is done, you can see that we have this BAD, KGA, so those are surely smaller than these ones. These ones are smaller than these ones, and these ones again are smaller than UZT, which are the biggest. So when everything is done, then everything is sorted, nicely sorted. So that's the whole idea of That's the whole idea of quicksort, and an example of idea of divide and conquer strategy. Okay. So that's simple, isn't it? The only stumbling block is how to do this step, which was deemed to be easy. Move everything what is big to the right. How do you know what is big and what is small? Because when they give you this array, it might be a big array, so when you look at the beginning, how do you know what's there inside? How do you know what is big and what is small, in fact? And to know what is big and what is small, you would need to sort it first and then choose some median, and that would be the divisor between smaller and big values. But before it is sorted, we simply do not know. And because we do not know, we more or less have to be a little bit statistical. That means we have to rely on luck a little bit. So, what the luck will say? The luck says, choose a pivot, some pivot value, we call it pivot value, and that pivot value will be will tell you what is big and what is small. So go into your array and just choose any value from your array, just any, and in most cases it will not be the biggest, it will not be the smallest. You might expect that it will be more or less somewhere in the middle of all values you've got in there. So its value will be more, not the smallest, not the biggest. And because this is more or less randomly scrambled, you say, well, then you can choose to pick the first one, or you may pick the last one, or you can pick the middle one, or you can pick the fourth one. It does not matter. You choose some pivot. Later we will see that it is important how to choose it. But at the beginning, let's say we have just some pivot. Somebody is pivot, and then its value will decide who is smaller and who is bigger. Everyone who is smaller or equal to pivot is deemed to be small, and everyone whose value is bigger or equal to pivot is deemed to be big. Now let's do this division into small and big ones. We do it in place, not using any additional space, so we must be careful and do it in detail. So what we do, we take two additional pointers, so IL and IR, left and right pointer and stars on the opposite sides of the array. And then we do all the time, now we will do the same stuff. We will compare the values which are under each pointer, and compare them not between them, but each of them we will compare with the pivot. So let's move to the next slide. Take the left value. That value is equal to the pivot. So what the left pointer will do, it will stay put. The right pointer will see something which is, that value to which it is pointing is smaller than pivot. So it will always, it will also stay put. Why do they stay put? Well, because what they intend to do is to swap the values to which they are pointing. The right pointer is pointing to something which is obviously small, and the left pointer is pointing to something which is surely not big. It is pivot just by accident. Now it is equal, so it is not big. So it is not. It might belong among big values. So what they can just swap those values between themselves, which is done here at the bottom of the picture. And when they do this, these pointers, they move one position inwards, each of them. And now recursively, the problem is in fact the same between the leftmost and between the rightmost element, because now we've got these pointers, each of them is pointing to something, and now they can continue their work. So continuing with our example, what's going to happen? The left pointer points to A originally, but A is smaller than pivot, therefore it can stay on the left side, because the left side belongs to the smaller values. So left pointer moves to the right, finds the next value, which is K, and K is also smaller than M, so again pointer moves to the left, left pointer moves to the right, finds D, D is smaller than pivot, so left pointer is moving to the right as long as as it sees small values. When it finds a value which is bigger or equal to pivot, it stops there. The right pointer does exactly the same stuff, only of course it is sensitive to sensitive to the values which are smaller or equal to pivot, and there it stops. So it's started a value z that's bigger than pivot, so the pointer moves to the right. Next is value u, which is bigger than pivot, so again it moves, and now it finds value which is obviously smaller than pivot, so now it stops. And when they stopped both those pointers, they swap their the contents to which they are pointing, and when R and J are swapped, so J and R there, and you can see we've got this part of array already, the leftmost part already contains small values, and the rightmost part contains big values. They are not sorted whatsoever, because in the beginning they were not sorted as well. But the important thing is that we are now creating slowly but surely creating the array which on the left has small values and on the right has big values. So now they continue, these pointers. They come to B, and you already know what will happen next. B is smaller than M, so left pointer will move to T, and it will stop there because T is bigger than pivot, and the right pointer is pointing to something bigger than M, so it will move to the right. There we find T, it is also big, so it will again move to the right, and the right pointer will stop at B. So that's exactly what happened. And now because they have met those pointers, in fact, so now they even passed each other. So now everything, you might be quite sure that to the left of the left pointer is everything. Those are small values, and to the right of the right pointer are big values. And there we are. So this condition says when to stop. When the index of the right pointer is smaller than the index of the left pointer. So we stop. And when we stop, we know that we can say, okay, and we can continue recursively, or the whole algorithm does that, recursively processes the left part, and after the left part is processed, it will process the right part. So and the left part is processed in absolutely the same fashion. You take the left and right pointer and let them point to the end of the segment of the array we are just processing. Choose some pivot. As you can see here, they always the first element in the array or in the segment, just for simplicity, choose some pivot, and then they just do the same stuff. So once more, it is there, left and right. What are they looking for? At left is looking at E, so it swaps with the right, because the right is pointing to something small which is smaller than E, so they swap it, they move inside, and so on. So that's more or less should be more or less obvious. And again, when they arrive to the middle, then again they pass each other. Therefore, again we've got a piece of array divided into small and big. So we take one of those and recursively continue until everything is perfectly done. And when it is done, piece of array is sorted, and then you move, or the recursion takes the next part of the array and does everything in there, and so on, as they say here. It's a little bit complicated, and the question is whether it is more efficient than the previous methods, because no one knows that. It should be more efficient. Before we talk about it, I just presented the code of the whole stuff. Surprisingly enough, it is not that much more complex. The pictures typically they are not that part of the code, so that is there. So there is the whole quicksort function, which takes this array as a parameter and also low and high. That is, they have the index of a currently processed segment of the array is the input, low and high. So at the beginning, low is 0 and high is the index of the last element in the array, and then of course as we go recursively inside, these are getting closer to themselves. So for what we do, we take a left pointer and set it on the left, take right pointer, set it on the right, and choose some pivot. In this case, they do it, they choose the first element. Maybe it is wise, maybe it is not wise. You've got some pivot, and what you do with the pivot? Now, this green part is this moving of the pointers inwards. So what's going on there? While left is to the left of the right pointer, this says that while this picture left is to the left of the right, while this is true, what we do, while left is, I'm reading two lines at once. This line says while true, of course. If left is bigger than R, so when they pass each other, the loop is broke, so you terminate the loop. While the left is to the left of the right, the action is still going on, and also there is one extra case. So and while, and now there is while and while. Again, the first is for the left pointer, the second is for the right pointer. And that is the left moves to the right while it sees the values which are smaller than pivot. So it leaves them there. So your small value, you are there, you are next small value, you are there, you are there. Something big, you stop. And then the right pointer kicks in and says, okay, I am seeing something big, something big, something big, and now there is something small. I have to stop. Now the left is standing here, right is standing there. They have to swap. So these two loops were just performed, and then in case after this getting close to each other, if left is still to the left of the right pointer, then they swap the elements and continue do that one step inwards because before the big loop is repeated. So this is this part is this swap here, and it happens only in case when left is smaller than the right. It might happen that I left and I right are pointing also to the same element. In fact, for example, if that element is equal to pivot, then it belongs to the left and to the right simultaneously. So both left and the right might happen to be pointing at the same element. And in that case, if they stop there, that means that that is surely pivot value. Pivot value must be pivot value in there. Therefore, it is the value which is between small and big. So everything what is on the left is either smaller, either equal to the value. Everything on the right is either bigger, either equal to the pivot value. Therefore, what remains in that case, the left part has to be sorted and the right part has to be sorted, and that value can live between them because it belongs there, so you don't have to move it anywhere. So that's this last line. It takes also care, as you can see, they are checking the values against the pivot. So it cannot help. What this implementation does, that it simply prevents when you start with this start configuration, this code prevents that one of the indexes runs out of current segment of the array. You might imagine that, for example, the left maybe rather right would be moving, and somehow even go past left, go somewhere outside. But that cannot happen because they are bound by this pivot. Whenever they stop at the pivot value. And always you find anyone is pointing to the pivot, then they swap the position of the pivot. So, for example, if pivot is equal to anything like 6, and you've got like 2, 6, 4, 9, 11, 8, 6. You want to sort this array, then you set left on the left, right on the right, and left sees 2, which is smaller than pivot, so it will be moved to this position, and right C, which is something which is surely not bigger than the pivot, so it also stops there. So they do additional stuff that they really swap those two values, although you would say that it is absolutely unnecessary when they are the same values. You have why swap them, but that is done because it makes the code easier. So this code is fine-tuned, even at the cost of doing this unnecessary swapping, you keep the relatively simple code. So this code works nicely when all the values are more or less different. If you got a lot of the same values in your array which has to be sorted, then of course you say, well, that it will not be that much simpler. So they say that this will slow down the sorting, of course, and it will. On the other hand, but not catastrophically, because, well, you still what you have to do is to get with those left and right pointers somewhere, make them meet. So you have to scan this array in any way, and swapping just adds some constant factor. On the other hand, when you are in quicksort, which has to be quick, then you really don't care not just about the asymptotic complexity, but just plain complexity. That means you want to minimize the number of any work you do, but that's a more complex question. So what's the result? The result is still not obvious, because we have seen, well, there is some idea, and maybe it works nicely, maybe it does not work nicely. So let's jump into picture, which is somewhere here. What does it do? As you can see, this is a depiction what's going on in your typical quicksort. And if you presume that the values are mostly different or more or less randomly ordered, then typically more or less it often happens that the small values and the big values, those sizes are somehow similar. Sometimes it is sometimes they go into extremes. So when they were processing the leftmost part of the array, they had to divide it into smaller and big values, and because obviously in this case again they chose a pivot to be the first element in the current segment. So that was pivot. So everything what is bigger or equal to the pivot is big, and that's only this one element. Therefore, that's only one big element, and all other elements are small. So if, for example, if you choose the smallest, the pivot to be the first element of the processed segment, then you might easily see that if you get a reversely sorted array, that will be a problem for the quicksort, and it will degenerate into something very slow. So let's have 6, 5, 4, 3, 2, 1, and let's choose pivot as this element. So what will happen that you set left and right pointers there, and this is too big, okay, but this is small, so you have to swap these two things. So 1 will go there, 6 will go there, left and right will get in, will make step inside. Now what left is seeing? Left is seeing number 5, which is surely smaller than pivot, so left is moving to the left, and of course leaving all those values on their positions. 2, and when it arrives to 2, it passes through and arrives at 6, and then that moment it stops at 6 because it is bigger or equal to pivot. Right is pointing to 2, left is pointing to 6. So now you go and you do this change, and what happens next? That you say, aha, so those are big, these are small. So big ones don't have to be sorted, but small ones have to. So you say, okay, put our, now I will just copy it once more to be able to process it. Put left and right on their positions, and if you want to be systematic and choose again the pivot to be the first element in the segment, so again what's going to happen should be more or less clear. Now left is smaller than left is, and that is our pivot. Left our pointer is pointing to something what is bigger, or it is smaller or equal. No, it is pointing to something what is bigger or equal to pivot. Therefore, a left pointer will stop here and will want to exchange it with the right. But before that happens, the right pointer says, okay, I have to do my work as well. So I'm looking at 2, but that is bigger than pivot. So they move to the right, and then they look at 3, that is bigger. Oh, that's bigger than 5, that's bigger than that. This is bigger than pivot. So IR, in fact, will arrive exactly to the position of where also left is pointing, and then there is this code which says, this implementation which says, okay, if they are pointing, both of them, if they are pointing to the same element, then we simply divide, process the stuff which is to the left. There is no such stuff, so that will not happen, and then we will extra process those. So those are small, those are there are small, there is pivot in the between, and those are big ones. And we are among big ones, and there is 4, 3, 2, and the situation will absolutely repeat itself because it is the same stuff recursively as it was here, 6, 4, 5, 3, 2, 1, there are 5, 4, 3, 2, so they are monotonely decreasing nicely, and again you will in each phase, your piece of the array, your segment size decreases only by 1. So there each step device segment, device current segment into 2 pieces, subsegments. No, I will not go into the 2 pieces, so small and big, small and big, and one of those has size 1, and one of those have the size nearly the same. Each step, the current segment of size, or length rather, of length k into 2 pieces, small and big. One of them has length 1, the other one, the other has length k minus 1, therefore. So in each step, we have to scan and to process the whole segment we have to process. Therefore, in total, we need total number of elements accessing or comparing with pivot. So total number of comparisons of comparisons in array of size n with that property that it is sorted in reverse order, or even it is if it is sorted, does not matter. Sorted might be reversely, sorted reversely, and taking pivot as the leftmost value of current segment and segment. So total, we are comparisons, comparisons, it looks like C. So total number of in this case, that total number is obviously at the beginning you have to scan everything, so you do n checks. Next you have to do n-1 checks, because you do it here. Next you have to do n-2 checks, and of course the pattern continues. Finally arriving to 1 check, maybe no checking, doesn't matter, maybe you stop when the size is only 2, but that does not matter because this is obviously n squared plus 1 plus n, excuse me, over 2, if I'm not mistaken, which is of course theta n squared. So in that case, if you apply the scheme which I've just presented to the array which is sorted, and you choose the pivot in the way which is that simple, then you easily arrive and you achieve nothing compared to previous sort. So what's the problem? The problem is, of course, that the pivot is not anywhere in the middle. So pivot remedies, what to do? Don't choose, just if you want to be sure that this does not happen, choose your pivot more wisely. So, for example, you can do it in that way, so choose it randomly. Randomly, that is at random position in your segment. So if you choose it randomly, then surely in very few cases you will choose. The process will choose either the first, either the last element in your current segment. So we choose it randomly. Mostly we will choose something inside, and that something inside in most cases will not be the biggest and the smallest element in your segment. So that choose randomly. Then how fast is your random generator? Maybe you want before you say random generator. It takes some time. It has to do some computations inside, and each time, who knows? So we take median of 3 values. First, last, middle. So anytime you are presented with a segment of values, you take the first value, take the last value, take some value in the middle, and take that one which is not the biggest of those 3, not those smallest of the 3, but that which is in the middle of those. So in that case again, you will avoid this situation. Well, but it is not while it is not completely guaranteed that you will avoid it. For example, if you go randomly, who says that the random process will not generate in each case? It will generate a smaller or the biggest value. If that happens, but that has low probability, because the probability that in the first round that it will choose the biggest one is 2 over n. So that probability is 2 over n. And if that probability happens, then you will be left with really, again, this unfortunate segment, which is just one element shorter. But then the next probability that it continues to be so bad is again 2 over n minus 1. And the probability that this unfortunate sequence of events continues is, of course, computed as the product of these fractions, and these fractions first are quite low, and when they multiply, they very quickly, the probability gets very low. So the probability that happens 10 times in all those, all that process, as you can see, is small. If your n is 1,000, so after 10 times it got 1,000 to the 10th power, which is 10 to the 30, but 10 to the minus 30. So that probability is very low that you will get totally unfortunate output. So that's more or less intuitive argument. We don't do exact, which would take much. That surely will take the whole blackboard to do it. So nevertheless, the argument is that random processing or random choice of the pivot is good. Again, the median, there is the same argument. Who says that first, last, and the middle ones are just those least favorable choices of root? But in most cases, it does not happen. So in real life, there are some extra. There is a linear method of finding not median of medians, finding value not too dissimilar to the median, Now that means there is, and if we have time at the end of the semester, I might present it. There is a method which reads the array once or two times, just few times in total, and find some value without sorting it at all, and find some value which is assured to be relatively close to the median, not let's say somewhere between 30 and 70%. So if you sort the array, you are guaranteed. So between the first 30 and the last 30%, you can find a value which is somewhere inside. Not the smallest one, not the big one, not the biggest one. But again, that takes a long time. So in practice, it's not good. And in practice, there are many other improvements to the quicksort. For example, if you look into your library, into source code of your sorting, you will find quicksort. But that, for example, they always do what they check whether your array is sorted or nearly sorted. Because if it is sorted or nearly sorted, they just don't use quicksort, and they resort back, for example, to insert sort. Because when it is nearly sorted, then it is in fact smaller to use simpler approaches. Now what then happens in general case? In general case, favorable case, when the array is divided more or less into halves, as it is there at the top, but I will just very probably redraw it a bit. They simply scan the whole array and divide them into small and big, and again the small are divided into small and small, big of those small, and of course the process continues. The segments of the array which has to be processed are getting smaller and smaller, and more or less uniformly they are the same. In completely ideal case, the division lines run in the middle. Now, how much work has to be done? When we start the quicksort, now you put there your left and your right pointer, and then you move them until they meet inside somewhere in the middle. Therefore, when you go there, your work you have to do is proportional to the length of the array in the first step. In the next step, you are working with only half of the array, and of course with small, and when you process the small, then you work with the big ones. But in all those cases, those again have to be processed. You put your left pointer on the left, the right pointer on the right, and you do it in all instances. That means when you look at it it again by levels, you see that this part of the array and this part of the array, no matter where the division is, have to be processed. And again, in this case, in all cases, you have to go through these values. And in fact, it is the same as if you, in the number of operations, it is the same as you went through everything once, because we have to do here, and then you go do here. So it is the same as when you go up there. So here the total again is the number of operations you do in processing this part, and this part is proportional to n. And the same is true for all other levels, of course, because you have to process this, process this, process this, process this, put together theta n. So this goes on, these recursive calls, and after some time they will stop, and after that we just total all the complexities of processing each level of this recursion tree. And how many levels are there? And now, of course, but if each time you divide your array into halves, that means that after logarithm of n, after binary logarithm of n steps, you will arrive at situation when the segment which has to be processed has length only 1 or maybe 2 or short, and therefore there the whole process stops and there's nothing more to do. So if the number of levels is logarithmic, and in each level you do work which is proportional to n, so then total is theta n times logarithm n, which is a little abuse of notation, but I hope it does not make any ripples on our algorithmic pond. So we arrive to this, and as everybody knows, logarithm is small number. So that says whenever we are more or less lucky, and it can be with nearly surely guaranteed. We are lucky. The quicksort will perform in time proportional to n times logarithm. And when it will not perform nicely, if all the values are the same, then simply this does not save you, this does not save you. You've got all the time you've got the same value, no, it will save you. In fact, if all the values are the same, what will happen if all the values are the same? We've got some. All the values are the same, so you put your left, you put your right. However you choose the pivot will be 4, and they will go from left. They say, 4 and 4, so they have to be swapped, and then IL is moved inwards, IR is moved inwards, and they will both go inwards, and they will meet in the middle, so they will divide it in the middle. Therefore, this situation will appear, and therefore the whole stuff will run in time, n times logarithm n. So that's the improvement. That's the improvement, because we can with little effort, and when we avoid some extra degenerate cases, we can sort our values in n times log n time. The last part of the slides, there are 3 slides which we have to quickly quickly look at. They are talking about stability of the sort. That's very simple. A simple concept. Stable sort does not change the order of elements with the same value. Therefore, if when you are sorting some array when there are some same values, the stable sort does not change the order of the values which are the same. So in sorted array, this first 6 will precede the second 6. No, it makes no sense when they are absolutely the same, then the stability is completely useless concept. But in case when this is a blue 6 and this is a green 6 and you want to have blue before greens always, that might easily be important. And the example is there, which I am going to present in the last minute. Somebody brings you a list of customers which are sorted, because of there some error, which are sorted by their first names. Yeah. So first there is all Andrews are there, and they are not sorted according to their second name, surnames. That's the order there is just random. But you might be quite sure that Andrews are first, then there are Barbaras, Charleses, Dominicas, I don't know, who is E? ECD, Dominicas, Eugenes, for example. I don't know, no idea. And then okay, and you want to fix it. So if you run stable sort, then you might sort only by these surnames, and the order then the order will be retained of what you already had. So if you want to sort it so that first comes all Amundsens and then Browns and then Cooks, so you sort only, you don't look at the first names, and the stable sort does this. Well, stable sort will take first Amundsen, then it will take next Amundsen and next Amundsen and put them at the beginning of the sorted array, and it will retain their relative order. So because there is Amundsen, we know by definition that the sort is stable, so the Andrew Amundsen will surely come before Barbara Amundsen. And the same, of course, holds for all other cases. So if you do that, then you don't have to check this part at all. You can just sort by this. You don't look at the first names whatsoever. Stable sort does that for you. If you, in the same situation, you use a sort which is not stable, which, as they here tell you, quick sort is not stable. If you sort only by these surnames, it will mess the order of the order. So Barbara Amundsen will come probably or maybe before Andrew Amundsen. It will come with probability 1/2 before Andrew Amundsen, but that means that we've got a lot of elements, so surely there will be somebody will not be in correct order. So therefore be careful what is a stable sort and what is not stable sort. And quick sort and selection sort. Selection sort is the slowest one we had at the beginning, so we are not that unhappy that it is unstable. Quick sort is always unstable. So again, some trade-off always is there. Quick sort is very fast, not stable. So you cannot use it on complex data. For example, you don't use it for sorting your objects, because you sort the objects by some keys, and their keys might be sometimes the same for different objects. And if you want to keep the original order of your sorted objects, don't use selection sort. Don't use, and always quick sort. Don't insert sort and bubble sort. are stable. They say they are more or less stable, so that means you can, when you implement them correctly, they are stable. You can implement them incorrectly, that they become unstable, but you have to strive to a little bit to make them unstable. But nevertheless, as you can see, this again another it's another let's say what it is. It's important part to consider when you think about choosing some sort for sorting your particular complex data. So that is it, and see you next time. We will talk about other sorts, again more faster, more complex, for more special situations. So thank you. See you next in the practices. Yeah, I'm completely sleepy by now.